Hi class. In this video, I will demonstrate how to do a hypothesis test for one mean using a randomization distribution. A bag of Skittles claims to have 61.5 grams of candy inside. We want to know, is there evidence that the actual mean weight of a bag of Skittles is different from the weight stamped on the bag? A random sample of 22 bags was selected, and the mean weight of the Skittles in the bags in the sample was 62.36 grams. So our first question is, what is the population parameter that we are interested in? So to figure that out, I look first at what are we measuring? And in this case, we are measuring the weight of the Skittles in the bags. And weight is a quantitative variable. So our response variable is quantitative, which means that we're dealing with means. So then I look at, okay, do I have one group, two groups, three or more groups? And I'm just looking at Skittles. So I'm just looking at one quantitative variable. So I'll put one quantitative, which means that I'm dealing with one mean. So when I'm defining my population parameter for one mean, that parameter is going to be mu. So the symbol for the parameter is mu, and the first word that should follow the equal sign is mean, since mu is a mean. So mu equals the mean weight of all Skittles bags, at least the size that I was using in this experiment. So mu equals the mean weight of all Skittles bags. Next, we want to know the best estimate for the parameter. So the best estimate for the parameter is really another way of asking for the sample statistic. And it tells us here that the mean weight of the Skittles in the bags in the sample was 62.36 grams. So this is my best estimate or my sample statistic. And the correct notation for a sample mean is X bar. So X bar is equal to 62.36. And you can throw grams in there for good measure if you'd like. Next question, what are the null and alternative hypotheses for this test? So the null and alternative hypotheses, they're always written about the population parameter, which in this case is mu. And the null hypothesis is statement, like the claim that's being made. So in this case, the claim that is being made is the weight that's stamped on the bag. So Skittles is claiming that their bags weigh 61.5 grams. So my null hypothesis is going to be mu equals 61.5. So the equal sign always goes in the null hypothesis. For my alternative hypothesis actually goes right along with my research question, which is there evidence that the actual mean weight of a bag of Skittles is different from the weight stamped on the bag? So the weight stamped on the bag, we already decided that's the 61.5. The mean weight of the bag of Skittles, we're defining that as mu. So the number in the null hypothesis and the alternative hypothesis will always be exactly the same. In fact, the only difference between the null and alternative hypothesis is the symbol. And we already know that the null hypothesis always gets the equal sign. The alternative hypothesis can either get greater than, less than, or not equals to, depending on the wording of the question. So here's what my question says. Is there evidence that the actual mean weight of a bag of Skittles is different from the weight stamped on the bag? Different from is code word for not equals to. So that's what I'm going to throw down here in my alternative hypothesis. So null hypothesis, mu equals 61.5. Alternative hypothesis, mu not equal to 61.5. So is this a one-sided or a two-sided test? Well, we can tell by looking at the alternative hypothesis. If it says greater than or less than, it's a one-sided test. If it says not equals to, it's a two-sided test. Ours said not equals, so that means that it is a two-sided test. And where the distinction becomes important is when we're finding the p-value, as we're going to see in a minute here. All right, so our next step is to find the p-value. And I've been given here a randomization distribution based on 500 samples. So how I use this is I am going to locate my original sample statistic on the x-axis. So I'm going to go back here. So it said my original sample statistic is this 62.36 grams. So here's my randomization distribution. I'm looking for where 62.36 would be. So this is 62, this is 62.5. So right in the middle would be 2.25. And then, so probably 62.36, I'm guessing would be somewhere around here. So 62.36. So this is my original sample statistic here. I'm going to draw a line even so I know right where it is. Okay, next, I want to count how many dots are more extreme than my original sample statistic. And by more extreme, I mean away from the center. So since I'm on the right side of the graph this time, I'm going to count all the dots to the right. If my original sample statistic would have been on the left, I would just count all the dots away from the center, which would be to the left. So here we go. I have 1, 2, 3, 4, 5, 6. So there's 6 dots that are more extreme, as extreme or more extreme. I know I have 500 total samples. So my tail proportion, or the proportion of values that are higher than my value here, is going to be 6 over 500, which is 0.012. Now, here's where that distinction between a one-sided and a two-sided test becomes really important. In a one-sided test, this tail proportion that I just found would be my p-value. But in this case, we have a two-sided test. So my two-sided p-value is double the tail proportion. So my two-sided p-value would be 2 times the 0.012, which is 0.024. So my p-value is 0.024 for this problem. Remember that our p-value is a measure of how much evidence that we have against the null hypothesis. The smaller your p-value, the greater the evidence against the null hypothesis. So in this case, my p-value 0.024. I don't really have a specific alpha level for this problem. So if you're not given one, we always use a 0.05 for the alpha level. And if I compare the p-value to my alpha, which is also called the significance level, then I can see that my p-value is low, lower than alpha. And when p is low, HO must go. So I'm going to reject the null hypothesis. And if I reject the null hypothesis, that means that I have sufficient evidence that my alternative hypothesis is true. And I'm going to write out the alternative hypothesis in words. So in this case, that means we have sufficient evidence that the mean weight of a bag of Skittles is greater than the weight stamped on the bag. And if you would have written the actual number here, the whatever it was, 61.5, that would be cool too. So hopefully that helps a little bit in figuring out how to do a hypothesis test using a randomization distribution that's already been given to you.